Hello. In this video, I'm going to review the first part of Chapter 8 for Modern Communications. All right, so the error correcting codes, they sit after you generate the data, like your favorite cat video, and before the modulation, which is the modulation maps the bits to pairs of voltages that then get massaged and then upconverted and sent out the amplifier and the antenna. So the goal of the error correcting code is to introduce additional information or parity bits, which allows us to reconstruct the information bits at the receiver. On the receive side, it's sort of going through the same process in some sense, but backwards. And the last thing we do is we decode the signal. And then by decoding, what we do is we try to correct for errors that might have been introduced by the channel. So we have discussed this before. If you make decisions a symbol at a time, what ends up happening is you get relatively poor performance that is far from the Shannon limit. And so what Shannon basically encouraged us to do, while Shannon did not tell us exactly how to do any sort of correction, but Shannon definitely encouraged us to consider lots of symbols at once and making joint decisions across many, many symbols. In fact, asymptotically infinite number of symbols. And so if you make decisions, on the other hand, a symbol at a time, you get poor performance. Now, potentially it's good enough for some applications. So here we have an example of just using a BPSK. So we get the probability of a bit error as a function of the signal to noise ratio. And if you make a decision symbol at a time, what ends up happening is in order to get to very low probabilities of error, you have to go to very high signal noise ratios. So the Shannon limit says above that SNR, you should get no bit errors or effectively no bit errors. But if you make decisions at a time, it's very slow. So what is good enough? Well, for some things, 10 to the minus fourth might be good enough bit error. But if you're trying to download an upgrade for your operating system, you want it to be 10 to the minus 15. Right? Any bit error could cause your computer to crash. So not nearly good enough, and you would have to go to incredibly high SNRs to get that sort of performance. So if we think about the error correcting code and the sort of the chain of things that happen, we start with our information bits, your favorite cat video. There's a high rate outer code, typically, not always. The purpose of the high rate outer code is to fix the few bit errors that are left over from the inner code, which basically does most of the heavy lifting. So while we're encoding, we take our information bits, we encode it with a high rate outer code. Then we do the inner code, like once again, as I said, does most of the heavy lifting. And then we often have an interleaver. Now, in principle, the interleaver does not need to exist because the channel should be independent, introduce the probability of error that is independent from symbol to symbol as it's going across the channel. The truth is it often doesn't work that way. Often errors are clustered in time or clustered in frequency. They're usually these sort of clustering of errors because there's something which causes a group of errors. For instance, maybe there's some interference that pops up and causes some number of errors. Not supposed to be there. It's not technically part of our model, but we still need to fix it. And so the interleaver spreads all those cluster errors out so it looks independent from symbol to symbol. And in fact, it then allows the error correcting to basically perform better. And after that interleaver, we do the modulation. That is where we map our bits into pairs of voltages, which then goes up and gets upconverted and sent out the antenna. It is important when you're thinking about this that you think about the focus on the information bits, the how much energy there is per information bit. When you add additional parity bits, for a fair comparison, you're sort of stealing some of the energy away from the information bit. Some error correcting codes allow you to directly see the information bits, and some of them basically kind of hide the information bits, so you don't get to recover them until the other end. We'll talk about both kinds of those codes. All right, so the error correcting codes allow us to approach the Shannon limit by adding these parity bits. These what basically is going on, you have a group of information bits that come in, you apply some function to it, and you get a larger number of bits on the way out. Lots of different kinds of error correcting codes. It's a whole field. Um, some 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 common ones are the block codes that we'll talk about, convolutional codes, which we'll talk about, and then various codes that sort of sit on top of those ideas, like turbo codes, and low density parity check codes and polar codes and other sort of algebraic codes. When you're doing decoding on the other side, you have a choice. You can do hard decisions. That is, you make a decision, a symbol at a time, of whether you think it's a one or a zero, or it's producing ones and zeros, and then run that into the error correcting code. Or a better approach is to calculate the likelihood that it's a one or zero and pass that likelihood information into the decoder. For lots of practical reasons, you might do one thing or the other. Typically, the error correcting code decoders that do hard decisions are computationally cheaper, and as a consequence, you can maybe you could save on power consumption. On the other hand, by using soft decisions, you typically get better performance, but it takes more computations, and so or it takes harder computations, more difficult computations, and so we sometimes decide it's definitely worth it because I'll get better performance, and sometimes you don't. It's an engineering choice. All right. So if you imagine some symbol sequence, and here I have sort of a projection on the two space of three symbols, but really we have some large number of symbols, but I can't draw it. There's the correct one, and then you have the correct vector, and then because of noise of some sort, it gets moved off, and you observe some other vector. And so what you're going to try to do is figure out efficient ways to sort of snap back to the correct vector. And sort of all these ideas are basically trying to figure out how we can do that in a relatively computationally inexpensive way. So that's sort of the focus of this. So let's start off with a super simple error correcting code. So this is a really weak one. So this is not error correcting code you want to use, but it's for pedagogical reasons we use this. Two, even for a weak code, this is not very good because it has some flaws, which we will use to sort of explain things along the way. So this is a short. This is a very short code, so it's not very good just because of that. But it's even worse than that. It's a flawed short code. So in this case, we're going to map two information bits into 5 bits. So you can think of that as sort of two information bits turns into 2 information bits plus 3 parity bits. In that case, we would say that this is a rate 2/5 code. That is, we have 2 bits of 2 information bits, but we divide that by the 5 total number of bits that comes out after the error correcting encoding. Typical or common coding rates are somewhere between 1/3 and 3/4. Lots of codes work in that regime, but there are ones that are sort of extend up to higher rates, which means they are in some sense not trying to correct too many things, or lower rates, which means in some sense that there are stronger codes. But the cost of the stronger code is you don't send as many bits through, information bits through, right? For every bit that goes through, there are fewer of them that are actually correspond to the information bits. In the end, you don't really think about the total number of bits. You just think about the number of information bits that have gone through. All right. So the implication of that, imagine that we have a symbol choice that we're using QPSK, for example. So with QPSK, in principle, we get 2 bits per second per hertz, or 2 bits per channel usage, and some complex channel usage. And so that means the number of bits that we can send through is equal to log base 2 of the four options. So that's the 2 bits per symbol. And if we have a code that's sometimes we use notation, a 7-4 code, or which total number of bits, comma, the number of information bits, in this case, a 7-4 code, that means it has a coding rate of 4/7. All right. So if we think about what the actual information bit throughput in this scenario is, we have we started out with the idea of we had 2 bits per second per hertz, or 2 bits per channel usage. But some of those bits are going to be parity bits. And so the actual information, the rate of information going through using QPSK then gets reduced to, in this case, 4/7 times the 2 bits per second per hertz, which means the spectral efficiency that's actually being sent through is 8/7. That's just 4/7 times 2, 8/7 bits per second per hertz, or 8/7 bits per channel usage. Now, of course, that's a weird number of bits, but we can average. You think about this using lots and lots of channel usages, not a single channel usage at a time. We're pretty focused on binary forward error correcting codes, and so that's what that's what we're going to talk about the entire time. But I did want to introduce the idea that binary or GF2 is not the only sort of coding approach. You can use different finite fields. And in fact, it's pretty common to use GF4 in convolutional codes. The idea there is, instead of just having a 0 or a 1, you could have four different symbols, not just 0, 1, but maybe we'll label them 0, 1, 2, 3 for a GF4. And sometimes you might want to do even more complicated Galois fields. But like I said, for everything we're going to talk about for this discussion, is going to be binary, or equivalently GF2. That is the two for the two options. There's a whole field around this. It's very interesting. But once again, we're going to be a little more focused and just use binary. And there are lots of examples of people actually using binary forward error correction techniques. So this is in fact more common than not. But at some point, if you look at this field for very long, you'll see other sorts of approaches using higher order Galois fields. All right. So one of the things we have to think about is how far apart different bit sequences are. And we typically discuss this in terms of Hamming distance. So, we're used to sort of Euclidean distances and some Euclidean space. That's just, the kind of distance we all know. When one position minus the other position, then take to draw a line about that, draw the line between the two vectors and see how long that line is. But when you're talking about something like binary, it's a little bit trickier to try to figure that out. In the end, it's super simple, as it turns out, though, because what you do is you just count the number of bit differences. All right. So if we take a look at the example here, what you see is what is the Hamming distance between the sequence 1, 0, 0, 0, 0 and 1, 1, 0, 0, 1. And so each step along that sequence, we're going to just ask the question, is it the same or different than the other sequence? So in the first position, it's 1 versus 1, and so they're the same. The second position is 0 versus 1. Okay, so that's a difference. And then 0 versus 0, same. 0 versus 0, same. 0 versus 1, different. And so the Hamming distance between these two sequences is 2. All right. So if we go back to that notional error correcting code that we introduced a little bit ago, we had 2 information bits. So that means there are 4 different possible sequences associated with 0, 0, 0, 1, 1, 0, 1, 1 information bits. And then those would map to particular sequences of bits of the encoded, well, we often call these code words, the encoded code word. So 0, 0 information bits maps to 0, 0 000. 01 maps to 01, 111. 10 maps to 10, 100. And 11 maps to 11011. All right. So what we can do here for this particular code is see what the differences between all the different bit sequences are. So the difference between code 0 and code word one and code word two. It's actually really easy to figure out since code word one is all zeros. So all we gotta do is count the number of ones in code word two. Clearly it's one, or sorry, clearly it's four. You add up a count four ones. If we take a look at the difference between code word one and code word three, well, code word three only has two ones in it, so that distance is two. We do one and four. Well, that's four again because there are four ones in there. Two and three, you actually have to look at. So between two and three, so the 0 to 1, and then 1 to 0, 1, 1, 1 to 0, 1 to 0. So that's four. Between 2 and 4, we see the first column, they got 0 versus 1, 1 versus 1, 1 versus 0, so that's 2, and then 1 versus 1 and 1 versus 1. So the Hamming distance between code word 2 and code word 4 is 2. And between 3 and 4, it's also 4. So why does this matter? If you imagine that in the receiver, you see some bit sequence, and remember what happens is a channel sometimes flips these bits. And so if it flips some bits, the channel going through the channel, can you guess which code word did it came from? What's the right answer? So for instance, if you send a code word out, the receiver, of course, doesn't know what code word was sent. And the receiver looks at it and recognizes that it's not a valid code word, right? So what is it going to do? What do we want it to do? We want it to snap back to the closest valid code word. All right. So it sort of depends on the direction that the air goes in. But you can imagine a scenario where if you had a Hamming distance of 3, like the cartoon we see here for the correctable version. So if it heads towards another code word, and the Hamming distance between the true code word and the other code word is 3, and I have a single bit error, well, then that means I can tell which code word I can say the closest distance to a true code word is going back to the right answer. If the Hamming distance is 2 and we move towards the code word where the Hamming distance is 2, we have a problem because now there's just one bit change to get to the other code word versus the true code word. And I don't know which one to snap back to. I don't know which one to pick. Right. So we say that there's no guarantee that we can correct that. So if we had a code where the minimum Hamming distance between different code words was 3, we could guarantee we could correct any single bit error. If we had a minimum Hamming distance of 5, we could guarantee that we could correct any 2-bit errors, right? And 7, we could correct any 3, for example. So it's in your interest to make sure that the code words are all as far apart from each other as possible. And that strengthens your code. It means that it's easy to tell what the right answer is. All right. So there are some more interesting things about the code than I had mentioned before. So this is a block code, or our example code here. It's a block code because it basically works in blocks of bits. As we already said, it's a code rate of 2/5. There are 2 information bits going to 5 total number of bits. And it has some other special characteristics as well, which are not always true. I can directly see the information bits in the code words. So the 00, for example, goes to 00 and then 000. Well, the information bits are expressed clearly in those first two bits, and we go down all the code words and we see that the information bits are the first two bits in the code word for each one of them. 10, for example, turns into 10100. So we have the information bits, and then we have some extra bits they're added on. All right. So we refer to this as a systematic code. All right. So this is a special code in the sense that it's a systematic code. But it has another structure which is also going to be useful to us, and it's also a special case. Once again, not all error correcting codes are systematic, and not all correcting codes are what we're going to say are linear codes. Now, the idea of the linear code is that if I add any two code words, I get another code word. So let's take a look at this. If I add code word 2 to code word 1, and we do this addition just along each bit in the column, there's no carry across columns. So if we add code word 1 to code word 2, well, code word 1 is all zeros, so you just get code word 2 back, right? So, well, that's not really surprising. Here's an interesting one. If we add code word 2 to code word 2, well, then we add the 0 to the 0, you get 0. You add 1 to 1. Remember, there's no carry, so 1 plus 1 is 0. And once again, 1 plus 1 is 0, 1 plus 1 is 1, 1 plus 1 is 0. And so what we get back is the all 0 code word. So code word 2 plus code word 2 is code word 1 because you get all zeros. So for a linear code, the all 0 code word is always one of the code words. All right, so we can go through and add other code words as well. Maybe the next interesting one is if we add code word 2 and code word 3. Well, so it's 0 plus 1, that's 1. And then 1 plus 0, that's 1. And 1 plus 1, wraps back around, that's 0. 1 plus 0 is 1, 1 plus 0 is 1. And so we get 1, 1, 0, 1, 1, which is the fourth code word. So when you add any two code words, you get another code word. So we refer to this as a linear code. All right. So we can take advantage of these special features and, in fact, have a nice way of generating code words from a simple structure, which is we say is a generator matrix. So you can use a generator matrix even if some of this stuff is not true. It doesn't necessarily have to be systematic, but that is you can see the information bits directly. But it turns out it's a very nice structure. So we're happy that it's systematic. All right. So the idea of the generator matrix is if I take information bits, express them as a row vector, and multiply it by the generator matrix, I will get the code word. And so it's also, if we have all the code words, relatively easy to build the generator matrix. What we have to do is go find the code words that will basically produce the identity matrix in the first part of the generator matrix, right? Because if we have just the one bit in the information vector, if we have the one bit of in the information vector and all the other bits are 0, it will basically pick out that row. And so that row will correspond to that code word. All right. So if the generator matrix has the first portion of the generator matrix is the identity matrix, then that's the generator matrix we need to produce all possible code words. All right. And so we can then decompose the generator matrix into two pieces. There's the identity matrix portion of it. That's the part that's associated with the systematic bits. And then there's a parity generating portion of the generator matrix as well. So now we can quickly produce the generator matrix if we have a list of code words. We just go find the first the systematic bits that once again are all the pieces we need to 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 build out that identity matrix in the first part of the generator matrix. So in our case, we know that the first part of the identity matrix is a 1, 0. So we just go look for 1, 0. And so that's code word 3. So the first row in the generator matrix for our example here is code word 3. To get the next row of the generator matrix, we need the 0, 1. That's the next part of the identity matrix. And so we go find 0, 1, which in our case is code word 2. And there we go. Now we have a generator matrix. So given those two code words placed in the generator matrix, it produces a generator matrix. We can then explore all possible values for our X as the information bits, 0, 0, 0, 1, 1, 0, 1, 1. And then we can generate all possible code words. So we can go back and forth this way. All right. Because of the structure, we can actually easily build a nice capability, which we call the parity check matrix. And the idea is there's some matrix that when we multiply the observed code word, so we take the observed code word, multiply it by this matrix, what happens is we will get an all 0 vector if it's a valid code word. And if it's not a valid code word, we'll get some vector which is non-zero. That vector we call the syndrome. So it's easy to actually figure out what this matrix must be. By tradition, we actually multiply, or we take the transpose of what we call the parity check matrix. So valid code word times the parity matrix transpose is going to be the all 0 vector. So this has to be true. This has to be true for all possible information bit sequences. So for that to be true, that means we got to get zeros no matter what the X is. So if we think about any valid code word is some sequence of information bits times G. Well, what that means is G times the parity check matrix transpose has to be the all 0 matrix. So and we can then figure out what that gives us. So if we go think back to that the decomposed form of the generator matrix, where there's an identity matrix and then a parity generating portion of the generator matrix. So that times some matrix has to be the all 0 matrix. Well, it turns out if we say H is negative P transpose times I, and remember we're going to take H and do the transpose. So that's going to be negative P over I. Well, I times negative P plus P times I is going to be negative P plus P, all zeros. And then the next observation we have is that for binary, addition is subtraction. So negative P is the same as P. So the parity check matrix then is P transpose I. So if you know the generator matrix, you can immediately write down the parity check matrix. All right. And this is worth just sort of discussing for a second. We're not really going to delve into this here, but it's useful for in the future if you think a little bit more about more advanced sorts of error correcting codes or error correcting decoding more technically, precisely. So if you think about the parity check matrix, for a binary scenario. Right, it has a number of ones and zeros. You can think about the structure being sort of the number of parity bits by the number of bits in the code word. And the connection between them is indicated by a one. So if there's a parity check, um, it can tell you what code word bits are connected to that parity check. So we can represent this as a bipartite graph where each one of the parity checks corresponding to the parity bits is on one side, and on the other side are the basically nodes that are associated with the code words, and they're connected if there's a one between them. So let's look at the first entry in the code word. It's 100, so it basically is just connected to the first parity check. We look at the second entry in the code word. It's 111, so it's connected to all three parity checks. And then the third entry in the code word is only connected to parity check one. And then the fourth entry is only connected to parity check two, and the fifth entry is only connected to parity check three. All right, so this doesn't really tell you anything right away, but I can tell you for some types of error correcting decoding, what happens is the information about our best guess on the code words is put in on the right-hand side associated with the code words. For soft decoding, often this is some sort of likelihood information. And then decoding happens by that likelihood information being passed over to the parity checks. The parity checks basically then look at all the likelihood information coming in there, and they might go, great, that's consistent with what's supposed to be. I'm going to reinforce that and tell everybody that, yep, you're probably right, and then pass it back. On the other hand, the parity check might go, you guys are a mess. What you're telling me doesn't make any sense at all. I'm going to say that it's less likely than you think it is and pass that information back. And by sort of sloshing back and forth on this graph representation, what will happen is information will flow across the code words through the parity checks. And hopefully you then get to converge to a correct code word. Once again, that's sort of beyond what we're going to talk about here. But just for sort of, if you run across this in the future, I wanted to expose this to you. So an early class of block codes, systematic linear block codes, are Hamming codes. So the nice thing about the structure of Hamming codes is that they are guaranteed to correct any single bit error, and they do that by having a d-min of 3. And so there's a whole bunch of them, and they have a particular size depending on the number of information bits. A not particularly strong version, but early on this was used all over the place when we just sort of really started using error correcting codes, is the Hamming 7-4 code. So it takes 4 information bits and maps it into 7 total bits. And once again, it's guaranteed to correct any single bit error. Now, if you have multiple bit errors, if the channel hands you multiple bit errors, well, you're kind of on your own, but it will correct any single bit error in that 7-bit sequence. All right, going back to our example. So we had our code example where we went 2 bits, which turned into 5. And then let's say we have some observed bit sequence. It might be a code word, it might not be a code word, because there might be errors in it. And what we can do then is take this observed sequence of bits and ask the question, is this a valid code word? By multiplying it by the parity check matrix transpose. So when we do that, we get what we call the syndrome. So the syndrome is the number of parity bits long. And if in this case y, which is we're asking is y a valid code word? If y is a valid code word, then s will be 000 in our case. So that doesn't guarantee it's actually what was sent, because you might imagine there were multiple bit errors and it might just have moved you from one code word to another code word. But we're starting with the hypothesis that we don't have lots of bit errors. We have some bit errors. We're trying to fix those some bit errors. And in any case, so valid code words for our case are 00000, 11011, So that's the top row in our syndrome table. And in any case, they will give you the all zero code word. Or sorry, all zero syndrome rather. Let's hypothesize that there is a bit error in the first entry. That's the second row of the syndrome table. So we could have picked a bit error any place. We're just picking the first entry because it sort of seems like a natural thing to do. We could have picked other bit patterns. It didn't even necessarily have to be a single bit error that we picked first, but we think it's likely that single bit errors are more common than double bit errors. There might be special cases where that's not true. But we're going to assume that single bit errors are more likely than double bit errors. So we're going to walk through single bit errors. All right. So if we have the single bit error and the first column, the first bit, then we get 1 0 0 0 0 if we'd started off with a all zero code word. If we started out with a second code word, then we just end up with the all one code word, and so forth. So you can see as we walk through the table that we have the bit errors, which you can probably see there in bold in this case. If you take any of these erroneous bit sequences and multiply it by the parity checks matrix, you get the 100 syndrome. Now, I don't think you could have predicted it was going to give you a 100. You just have to actually calculate it. But the fact that it is going to give you the same syndrome, no matter which code word you started with, it's only a question of what is the error pattern. That's important, and it's related to the fact that this is a linear code. So we can think of the error pattern as or you can think of what we received as a code word plus an error pattern. All right. So when we take a code word plus an error pattern and multiply that by the parity check matrix, well, the code word times parity check matrix is going to be 0, the all 0, plus the error pattern times the parity check matrix transpose. So clearly the only thing that matters is the error pattern, because the code word portion of it is just going to give you the all 0 contribution. So in some sense, all you have to do is look at what happens to the all 0 code word, evaluate what the syndrome is, and then that tells you what the error pattern is. So as I said before, if we have an error in the first bit, that gives us the 100. So let's try the second bit. And if I have an error in the second bit, I get the syndrome 111. Once again, I probably couldn't have predicted that. I just have to go calculate it. The next thing I would want to do is go say, well, let's hypothesize a bit error in the third column, or the third bit of the code word. So that would give us a 00100. The problem is, if we go evaluate that, we will evaluate it to syndrome 100, because that's the same as a bit error in the first bit for the code word C3, right? And so that syndrome is already taken, and so it was a weak code and it's a flawed code, right? We know that it has a dmin of 2, and this is what we're seeing. I can't guarantee that I can fix all single bit errors. So I'm either going to fix the bit error in the first position or I'm going to fix a bit error in the third position, but I can't guarantee that I can fix them both. And that's just a problem we have. All right, so I'm going to skip it. Now I'm going to go say, well, let's go take a look at a bit error in the fourth entry, 00010 now. And so we evaluate the syndrome and we get 010. And then we can go evaluate this for a bit error in the fifth position of the code word. We get 001. All right. So because we have three parity bits in this case, there are eight possible outcomes. The all zero syndrome is, of course, it's a valid code word. So that means we have so because there are three parity bits, syndrome length is three. So two to the third is eight possible sequences. The all zero one, of course, is already taken. So we can try to fix seven different error patterns. So we already tried to fix a bit error in the first entry, second entry, couldn't do the third entry, fourth entry, and fifth entry. So that means we still have some other things we can try to fix. So let's try to fix 11000. So the first two bits are in error. Go evaluate the syndrome. It's 010. Sorry, it's 011 rather. So that's a new syndrome. All right, we can fix that. Let's hypothesize another one. The natural thing to do would be to pick 101. We're just marching through and picking things. Except that's an actual valid code word, and we already know what the syndrome is. It's zero, all zeros. So that doesn't really help us. So let's skip that. And let's move to the 10010. So that's a bit error in the first position and in the fourth position. Go evaluate that. That's the syndrome 110. That's a new one. All right, we're good. So now let's go to the next logical one of 10001. Once again, it's a new syndrome. And now we've run out of syndromes. Now, the exact choice of what bit error patterns you try to fix is kind of up to you. We could have tried this in a different order, and we would have gotten a different set of bit error patterns that we can fix. We just kind of marched through in what I think is a moderately logical fashion, but it's not the only way we could have marched through error patterns. We clearly are not fixing all double bit errors. We've just got a few of them, three actually, specifically. The most double bit error patterns we're not trying to fix, but maybe we'll get lucky. So if we fix some extra ones, we fix some extra ones. And because dmin was 2 in this code, importantly, we couldn't both guarantee that we could fix an error in the first bit and the third at the same time, which is annoying, but that's life. All right, so if you evaluate something and you get a syndrome, so let's just say, for example, it's you get a syndrome of 111. Then we know that our best guess, given the way we built our syndrome table, is that the error is in the second position. So whatever we received, we flip the bit in the second position. Because the first two bits are the information bits, we just read off those bits after the correction, and that's our corrected information bits. And if we're lucky and things have gone well, then we have fixed the bit error that was introduced by the channel. All right. So I'm going to stop here and break this, and then the next part we're going to talk about is convolutional coding.